So we continue with our discussion on diffusion through the grain and grain boundary, and in that context, if you remember in the last lecture, I introduced a parameter, effective diffusion coefficient, and this is necessary even though for a single material, as I have indicated, the diffusivity through the grain boundaries could be substantially larger than the diffusion through the lattice. And so these are grains of a polycrystalline material. So therefore, in that context, I have shown that the effective diffusion coefficient, that derivation I have done, okay, and that could be equal to the lattice diffusion coefficient, means the diffusion coefficient of the bulk material. That's what is this particular material. And then we have a parameter which is 2 times delta divided by W, in which the W could be an average linear dimension of the grain, and delta could be the thickness of the grain boundary, and that this comes out when we have dealt with an idealized and this is B times boundary or GB. So this is the lattice diffusion coefficient, and I have shown that this factor is approximately equal to 1. On the other hand, the coefficient of boundary or grain boundary diffusion coefficient is 2D by W. Now this W, as I have indicated, is the linear dimension, an average linear dimension of the grains, and in the context of that idealized demonstration where I have drawn a 2-dimensional square grain, W was taken to be one of the linear dimensions. Okay, if you would have considered a spherical grain, you could have taken W to be equal to the radius. So it's a very simplified analysis just to show you and to explain to you that what are the significance of the parallel fluxes that we have tried to address. And this is an application area, and there we see that it is not just the lattice diffusion coefficient which can predominate, because the boundary diffusion coefficient is multiplied by a parameter where W is very, very large, okay, in comparison to D, delta, okay, is therefore implies that this factor vis-a-vis the entire factor will determine that which of the 2 parameters are determined. So even though, this coefficient is much smaller, delta by W, okay, this coefficient is smaller, and this coefficient here is 1. Even though the coefficient is larger here, that does not necessarily mean that the lattice diffusion will predominate, because of the simple fact that the boundary diffusion or diffusion through grain boundaries, because of the structural inhomogeneities present in the grain boundary, could actually turn the ball to other side, okay, or take the ball to the other side. So as a result of which, this typically essentially shows you the consequences of parallel diffusions, that if you have diffusions taking place simultaneously through the bulk material and through the grain boundary material, one can of course isolate it. If you perform a diffusion experiment with a single crystal, then obviously you will not see the effect of any grain boundary diffusion, and then you can isolate this particular parameter. But whatever diffusion coefficient for a polycrystalline material we quote, that diffusion coefficient is essentially a consequence of the lattice diffusion coefficient and the boundary diffusion coefficient. This is an important point that you must remember. So we move on to the next topic, which is the uphill diffusion. Now, as we have formulated the Fick's law, we have written it in terms of the concentration gradient, and then say that the total flux when there is no bodily motion which is involved is equal to the diffusion flux, and this is equal to diffusion coefficient. And if you say A, so this is in which X represents, or I will say, let us write it as Y, because capital X sometimes we used to represent mole fraction. So this represents the concentration gradient, kg per meter cube, meter square per second, and this is the flux, kg per meter square per second. So the total flux is equal to the diffusion flux, is equal to this, the Fick's law, according to Fick's law, when there is no bodily transport involved. Okay, and this can also, so this tells us that from a region of higher concentration to a region, material will flow from a region of higher concentration to a region of lower concentration. That's what is essentially it implies, and this I have already shown in terms of the concentration gradient, and diffusion is in this way. The net material flow is along the direction from a region of higher concentration to a region of lower concentration. But this may not be necessarily true in metallurgical systems, particularly those systems which are multi-component in nature, and that I want to illustrate. I can show that in terms of the meaning of uphill diffusion is, this is a downhill, okay? You are going hilltop, lower part base of the hill, but if the diffusion takes place in the reverse direction, opposite to the concentration gradient, in that case we will say the phenomena is uphill concentration. But how it is possible that from a region of lower concentration mass can flow to a higher concentration, and that is what I would like to address in a subsequent discussion. Let us consider two alloys of iron. Okay? One is Fe containing 0.44% carbon, and this is the famous experiment of Durkin, I think close to 60 or 70 years back, and this containing silicon content is about 3.8%. This percentage means essentially wet percentage, and the other is Fe containing 0.48% carbon with no silicon at all. Now, if you look at this, so what we consider now is a diffusion couple. If we have an alloy and then we join the alloy, this is one bar of the alloy, and then we have joined, so this is, that is what it is, and we have considered, so this is alloy 1 and this is alloy 2. So if you look at time t is equal to 0, then this has a concentration of 1 is 0.44, so I will draw it exaggerated figure. This is the concentration, uniform concentration. On the other hand, we have a concentration here which is this axis is the distance axis, okay, and this axis is the carbon concentration axis. So this is 0.48 and this is 0.44. This contains silicon and this does not contain silicon. Okay? So in this way you can go to, if you label it, then percentage carbon is this way and distance is this way. And you can say x is equal to 0. It's this. At high temperature, when they are of the same temperature and you want to maintain it at an isothermal, that is the experiment. So under isothermal condition at a high temperature, when both of them have equal temperature, and if these two materials are going to join, as far as the fixed law as I have written here, it will suggest that from a region of 0.48% carbon, material will flow to 0.44, because this is higher concentration region, has higher concentration carbon, and this is lower concentration carbon, so the material will try to flow in this direction. But what we are going to see, or what Durkin saw, after 13 days of keeping the two couples, diffusion couple in contact, and then separating them and looking at the microstructure, very interestingly, he found that the graph has become something like this. What does this indicate? That, so these are the solid lines that I have drawn here are the concentration profiles of carbon after a span of 13 days. That is what Durkin found out, and these are all based on his discrete composition, carbon composition measurements. Uniform concentration was horizontal, as the line indicated, and then by taking samples, these were found out to be the concentration. What does this indicate? If you now find out the average carbon concentration, obviously in this part I have now average carbon concentration is going to be percentage carbon at 13-day average, okay, is greater than percentage carbon average at the 0th day. So that's what it is. Because you see the concentration has increased. So if this is 0.48, this could be about 0.52 or 0.51 or something like that. If this is 0.44, then this could be about 0.40 or something like that. So what happens here, similarly, here I would say that percentage so 13 into second, I'll write it like this, 2, or this is second, that's better, then there is no confusion here, okay. So this, and similarly if you say percentage average carbon on the 13th day, 2 is less than percentage carbon average on 0th day in sample 1. So what does this indicate? This indicates that there has been a net flow of carbon in this particular direction, which essentially is opposite to the Fick's law. Okay. Now, why does it happen? You remember that, as I said, that this contains 3.8% silicon. Silicon, what it does? Silicon increases the activity of carbon. So this is now a multi-component system. This is a two-component system, carbon and iron. Iron and carbon have strong affinity with each other, so they form strong bond. Now, the moment silicon comes, iron-silicon bonds are also quite ferric, iron silicide. Iron has a great affinity also, equally strong affinity for silicon atom also. So as a result of which, what happens, in the presence of silicon, the carbon is not very comfortable. It wants to leave the system, and the activity of carbon is actually increased. For example, if I use, say a material or an alloying element which is a reverse effect, okay? In that case, the activity of carbon actually can be reduced. So there could be, suppose for example, I use here instead of silicon, say strong carbide forming elements like niobium, tungsten, etc., then whatever I am saying is going to be reversed. So the activity of carbon now is going to be even down from the activity in the original alloy, because carbon now finds that it is friendly with iron anyway, that is there the scenario on the other side also, but it now contains a better friend like niobium or tungsten, which even has a greater affinity towards carbon. So the carbon is not willing to leave the system, its activity therefore it's not visible at all. It is in very quiet condition, as if tied up very friendly with niobium or tungsten atom, so the activity can go down. Now, in multi-component systems, the presence of an additional solute. So in a two-component system, if you add a third element, that third element can increase the activity of the other constituents or decrease the activity of the other constituents, and it depends on the relative strength of the bond forming between various constituent elements. In this case, silicon is such that the presence of silicon does not allow much iron-carbon bond to. It's like, so you can visualize it. I typically explain in the class like if you have, some kind of a person, Dada kind of a person, in a colony, you will not see another Dada visible there because he will have the apprehension of getting beaten up. So silicon will not try to enter this system. Carbon will not try to enter this system. Carbon will have a greater tendency to leave the system. And increasing of activity of carbon due to the presence of silicon actually causes the flow of mass in the reverse direction in contrast to this particular. So we can say that, look, this is better for us to write that we can say is the molar density, and then we can say the activity of A is dy. This is possibly a better expression for a multi-component. We will not use, because in multi-component system, as I said, this kind of a behavior we will not be able to predict or do calculations on the basis of the standard Fick's law expressed in terms of concentration as the dependent variable. So the more important thing is that, as I said, that the diffusion takes place from this side to this side because the activity of carbon is greater than, in one, is greater than the activity of carbon, even though the concentration of carbon is smaller. And that activity gradient is actually causing the mass to flow, and hence it is legitimate to replace this activity coefficient by, concentration gradient by an activity gradient within the system. And if you leave it, so the equilibrium, just like the way if you have two different materials at two different temperatures, or the same material at two different temperatures, the equilibrium state is that if they are only exchanging not with the surrounding but with themselves, that the average temperature is the equilibrium state of temperature. If one object is at 100 degree, the other is at 200 degree, then possibly if you leave them together, the equilibrium temperature, and it's a adiabatic process, is going to be 150 degree. One gains 50 degree, the other loses 50 degree. So everywhere you find temperature has become after some time 150 degree. Similarly, here also, if you look at, after a very, very long time, you measure the activity, you will find out the activity here, activity here, activity here, activity here, across it is going to be same, but the concentration profiles are not going to be same. Okay? Because we are talking about a multi-component system, and that is basically the uphill diffusion process, and therefore we would say that to analyze a scenario where there is single component to two component system where the activity reduction or activity enhancement is not so significant, this expression would suffice. But if you are to deal with a system where there is alloying elements which can dampen or enhance the activity of the other solute elements, perhaps it is desirable to use or formulate the Fick's law in terms of activity rather than in terms of concentration. The next topic I want to tell you is, we're learning many things gradually, so we see also how difference, even though the mass fraction is a scalar, concentration is a scalar, temperature is also scalar, Fick's law versus Fourier's heat conduction equation are very similar. There are certain intricacies in mass transfer problem for which you do not find a counterpart in heat transfer problems, and that needs to be really understood properly before we can have a complete phenomenological description of the mass transfer process. One important effect, this of course we have discussed in the context of same phenomena, basically we have discussed in the context of mass flow rate or mass transfer for a gaseous species, and this I am going to demonstrate with respect to a solid, that if you remember I told you about in the first lecture, I think, mixing of two gases, and I said that on top of the diffusion of A into B, there may be a overall movement of A also. There is a bulk velocity may be superimposed on A depending on what are the characteristics of A relative to B. If A is lighter than B, then A will have a natural buoyancy tendency to go, and also the atoms itself can push, bulk motion of the large amount of atoms can actually push the B atoms and may not allow us to find out the diffusion velocities or the diffusion flux of BA explicitly unless we address this bulk motion component. And that's what I said, that when we will deal with gases, we will not use the Fick's expression, but we will have a generalized mass transfer expression where we will say that the total flux is actually total flux minus the bulk velocity flux, so the flux associated with the bulk velocity is equal to the diffusion flux. So that is an exercise that we did in B, and of course I have shown you that for equimolar countercurrent diffusions, this scenario will be exactly equal to that the bulk term will cancel out and pure diffusion case as in solid is going to be analyzed. Now in solids also we can experience the bulk motion, but that bulk motion we term in the solids as a drift. So here we have said in the context of drift is there is a bulk velocity, which is a mass average velocity. In this case also we will say it's a mass average velocity, but the terminology in the context of Kirkendal's effect, which we discuss with respect to solids, we will term as drift velocity. Now, what happens is, for example, and this is very easily explained because I want to introduce a term called interdiffusion coefficient that we'll see how that is the whole objective, to demonstrate what is Kirkendal's effect, what is drift velocity, what is the similarity between Kirkendal's effect in solid with the bulk motion thing that we have discussed already in the context of gas and modified the generalized and derived the generalized diffusion equation. And by discussing this, I will like to introduce the concept of an interdiffusion coefficient. We have learned about a diffusion coefficient of a species, we have learned about an effective diffusion coefficient, and the third type of diffusion coefficient that also you will be exposed to when I finish the discussions. Now, this is applicable to systems which has complete solid solubility, say copper nickel, we know they form isothermals, or even in oxides, magnesium oxides and nickel oxides, they form solid solutions. Now, if you look at the diffusion coefficient of copper vis-a-vis nickel, you find that the diffusion coefficient of copper atoms diffuse much faster than the nickel atom. So, if you make a copper alloy diffusion couple, for example, pure copper as opposed to pure nickel, the copper atom at a high temperature, of course, because you want to study the diffusion, and diffusion is a process which will not be quite rapid at low temperature. So, at high temperature, if you join two pieces of copper and nickel, okay, the copper, because it has a very large diffusion coefficient, at least 100 times bigger than 50 to 100 times bigger than the diffusion coefficients of nickel, as a result of which what happens, the rate at which nickel flows into copper, okay, is substantially lower with the rate at which copper starts to flow. So, the movement of the copper, rate of movement of the copper atom is much larger because the diffusion coefficient of copper is larger. Suppose this experiment was performed by putting in a marker, for example. Now, one can put several, these are non-interactive wires, for example. So, copper nickel, you can have a very fine wire, maybe of the order of micrometer diameter, which will not interfere chemically with copper and nickel. So, you can have platinum wires, for example. Okay? And now, if you allow the diffusion to take place at high temperature for several hours, one finds that this marked lines, they have actually moved to different places. They are no more here. So, the dotted line indicates the new position. So, you perform the diffusion couple, you join them together, allow the migration of copper from left to right and nickel from right to left, and these markers that you have posed. So, you can put it at the interface also. It is very easy to put it on the interface, okay? And therefore, you can see that these markers or the metallic wires that you have used to trace the interface, okay, this interface really has moved along the right direction. And this is because there is a net movement of the copper atoms. Copper is trying to diffuse fast, okay, through the medium, and as a result of which the markers are not staying in their original location, but they tend to move from left to right. And if I would have had copper on this side and nickel on this side, the same markers could have moved in the reverse direction itself, which essentially tells us that look, there is, rather than diffusions, on top of diffusions, there is a mass movement of the atoms from this from left to the right, and that mass movement from left to right has been termed as drift velocity, and that happens when you have large difference. Suppose had the two couples have same amount diffusivities, in that case what happens? The net velocity from left to right and right to left would have been same and the markers would not have moved. So this movement of the marker will be visible provided you have great difference in the value of diffusion coefficient of the two species, and fortunately we can have mixing at all composition in the solid state. Okay, so the atoms can migrate freely, and here we are talking about the diffusion coefficient of copper much greater than the diffusion coefficient of nickel. Okay, that is an essential condition. Now let us see how we mathematically treat this particular problem. So the Fick's law, if you use second law, as we can say, suppose we say, we'll write it not as copper and nickel, we'll say this is A and this is B. That's standard notation. So this is what we have, one-dimensional so if this is my y direction or x direction, I would say, okay, then diffusion, one-dimensional diffusion gives us, because the concept I'm trying to illustrate, unnecessarily taking two-dimensional scenario is not important. So this can be done with respect to a one-dimensional problem itself. So dA, the diffusion coefficient of A into B. So I will not write A into B. So I will write dA, which essentially means the diffusion coefficient of A in B. If I write dB, then I'll say it is diffusion coefficient of B, and then we have Ca. So I have not used activity here, because that is, the activity is equal to mole fraction, and also it is a unique material. There is no alloys, this is not a multi-component system, so the concentration equation, suffices. I don't have to use activity to write down the equation. So this is what it is, and this is actually that we all know from Fick's law, and this is J of A, and this we will write it minus N of A. Now this is the Fick's law, according to Fick's law, so where pure diffusion takes place, but we will not write this. Okay, we will instead write this, because of the simple fact that, as I have indicated, that there is a net mass movement, mass flux from the left to the right because of the drift velocity. So therefore I will write that on this particular direction, the net movement or the net flux is going to have two different components. One is the diffusion component and the other is the bulk velocity. And if we write this, in that case we can say that this is C, the concentration, molar concentration, and then we have this dTc. That's what it is. Okay. So this is the molar diffusion flux, and this is the bodily transport term, and V bar here represents what I have told you, that is the V drift velocity, and the definition of this is exactly identical to what I have discussed in the context of. So it's a molar average velocity if you are dealing with molar fluxes. So therefore we have the equation now. Systems operated with large various, in diffusion couples, large differences in diffusion coefficients, I think it is better not to use this expression, but to use Na, and instead of Na, don't just use Ga or the diffusion flux, but also consider the drift flux which I have. So since this is associated, this is also a flux. Okay, if you say it is kg per meter cube, multiplied by velocity, so this becomes a mass flux, and this mass flux is associated with velocity v, so this we will call as a drift flux. So in alloy systems where we have constituents diffuse or constituents have largely different diffusivities, it is desirable to include the effect of bodily transport term rather than using a pure diffusion expression. That is what is the whole objective. So this is now the equation. So we have so did I write it? Okay, yeah, x, everywhere x, so I will write it x not y, and then this is exactly the same equation I should be able to write for B also. And this is the drift velocity, which is all A, B velocities, the velocities combined. If you have two components, so the definition of V bar here is molar density Ca into Va plus Cb into Vb. That is what is the definition of molar average velocity. Since C is equal to Ca plus Cb, so therefore we understand that is equal to this condition applies. So if we add these two equations, then what we get? We will get minus, I will just omit one or two steps and then write you the final. If we add this and apply this particular condition, then we will get minus dA dCA dx plus V bar Ca plus dB, because I have transposed it to the other side, dCb dx minus V bar Cb. And so I am trying to now find out an expression for the drift velocity in terms of the pertinent variables. So if you look at that equation, so I transpose all the V, so V bar is equal to Ca plus Cb, and that is equal to, we have dA diffusion coefficient, and then we have plus dB dCb over dx. And therefore, V bar is now equal to, we have say 1 by C into dA That is the expression for V bar. Let me now substitute that expression of V bar here. Okay? So I bring it here, so I raise, so I have Ca here, and then let me put the expression of V bar, which is equal to 1 by C dCA. Okay. So this is dB, and then let us now manipulate this term. If you say, if you multiply So this can be written as Ca by C, which is equal to, actually I can write down Ca by C, and that is equal to my capital Xa, the mole fraction. Similarly here also I will have, so I will have Xa. Now from the condition we can also say that, look, this term, the derivative of concentration Cb with respect to x, is exactly equal to minus, and then because I have already stated that Ca plus Cb is equal to C, and if you differentiate, then obviously this equation comes to them. So now therefore this term goes here, because Ca, we have, there was 1 by C and the Ca with Ca multiplied, so Ca by C, that becomes Xa. Similarly with this term also, Ca by C is Xa, and then I have changed the sign here from plus to minus I have made, because instead of B I have written A. Now let us see that what it is. So if you see the terms now, okay, so we have dA, and then we have, therefore if we operate with this term, then we get dA into 1 minus Xa. And then here we have what? We get so we bring it here Xa, so into dA, so dA into 1 minus Xa, and then I think I have made a mistake somewhere. This sign should come out to be actually positive here. So I think somewhere I have goofed it up. So this, if you check the derivation earlier, because I have erased it, I should not be able to. So if you do this substitution here, this sign should have been actually, I think, positive here. 1 is negative, this sign should have been positive here. So you just check the derivation, and this sign should come out to be positive actually here. And then we have positive, then we have Xa times dB into dC by dx. That's what it is. But 1 minus Xa is equal to Xb, because it's a two component system. So we have dA into Xb. So Xb, mole fraction of B into diffusion coefficient of A, plus mole fraction of A into diffusion coefficient of B, and dx. And this parameter is known as the interdiffusion coefficient. It is not like the area average. You see there what happens? As yesterday I have said, the volume fraction of A multiplied by the diffusion coefficient of A. But here what happens is the mole fraction of B multiplied by the area diffusion coefficient of A. So there is an alternative, suffixes, and similarly Xa into dB, and this we notate the notation here is dA sub B. And you can see now that the Fick's law, to treat the system, if you want to study such systems, then the Fick's law expression should suffice. Interdiffusion coefficient, okay, and there should be here, if it's, I will say, write it like this completely. So there is a 1-to-1 similarity now. Only thing is that we have replaced the diffusion coefficient of A. So if you take a copper nickel system and we want to study the diffusion rate of copper and nickel and use only copper's diffusion coefficient in nickel, okay? So if you use d copper instead of dAb, then we will not get the correct result. We have to use an interdiffusion coefficient, and then only if we solve this one-dimensional equation with respect to the boundary conditions, the correct profile of copper, or the current concentration of copper, will come out as a function of. So we can then predict Ca as a function of t and x. So in such systems, AB, A and B, where there is a large difference in the diffusion coefficient of the values. So therefore, what I am suggesting is that don't work out the implication of the Fick's law, second law of Fick's, or the mass conservation equation based on individual species diffusion coefficient, but use an interdiffusion coefficient. And if you use interdiffusion coefficient in such equation, apply the correct boundary conditions, you will solve this equation and get the concentration profiles as a function of time and x, which will exactly match with your observation. But if you use, instead of DAB, only DA, in that case misleading information will come and the theory will not match with your experimental observation, which you can measure. Now, with this, we now want to move on to the solution of the steady state equations. One single parameter that we have used, I have written all along the equations in Cartesian coordinate system, but we can also, as you know from your heat transfer fundamentals, we should be able to write the equations in cylindrical and spherical coordinate system also. Now, if you look at, say, the diffusion from a sphere, steady state diffusion from a sphere having the radius r0, and suppose mass is coming out of it, okay, and at steady state, you can imagine possibly it's the same scenario as when you put some mothballs or naphthalene balls into your closet. So if you come after 10 days, what you see that the cupboard is completely filled with the aroma of naphthalene, okay, and the ball has shrunk in size because of the loss of vapor. But in this case, we are not considering that change in the size. So it is, I am considering that it is say RA and diffusion of A in a medium B. That is what I am considering. Okay? So my domain of interest is here. From, if this is the R radial reaction, then R greater than equal to R0 to R tending to. That is the domain of my interest. I want to find out if something is coming out, some mass is coming out, how is the distribution of that mass in this particular case. And because it is a diffusion not within a solid medium, it is a fluid medium as we are saying, and therefore this equation will apply. Na, as you know, is going to be is equal to minus CD, this is the diffusion flux, okay, I will write down this, XA and then we have XA into Na plus Nb. This is our generalized diffusion equation. Of course, you can say that two simplifications are possible here. We can say that B is stagnant, then Nb is equal to 0. So my flux becomes equal to Na is equal to minus C D. C is the molar density, this is the diffusion coefficient of A in B, and this is equal to one minus X. And this applies for stagnant medium. Another simplification is possible, even if we do not consider a stagnant medium, if you consider that the rate of mass transfer from this is very low, it is a low mass transfer problem, so therefore naphthalene, for example, is a case of extremely high mass transfer rates. The naphthalene ball in no time left in a cupboard vanishes, the size decreases. But in this case we may consider, to show you another simplification, that the concentration of A is going to be very, very small, because this does not lose too much of a mass as such. In that case, we can say that this small fraction A, okay, although there is the gradient of mole fraction, but the absolute value of the mole fraction of A is extremely small. That essentially shows that from here not much mass is flowing. But I am not saying that the gradient along the r direction is saying. If x is small, in that case Na becomes is equal to minus C d A x A. It's a case of pure diffusion then. Okay? So that the surrounding medium is stagnant, but there is a bodily movement part. This 1 minus x, where from it has come? This has originated from this particular term. And this term, what is the origin of this? This is associated with the bodily movement or the bulk velocity. So this 1 minus x factor essentially tells us that there is a bodily transport term associated on top of the diffusion itself. But when the concentration is x is small, in that case A is not going to move with a very high velocity, so the velocity itself will become small, and therefore this term can be neglected, and this becomes a case of low, or we say sparingly soluble material. A is sparingly soluble in B. So two different possibilities are possible, and if you want to now take a small, this is the same type of exercise that we have done in the heat transfer problems. So now we have the total flux Na, and so this is the input, this is the output. So I would say if this is R and this is R plus delta R, an elemental control volume having a thickness of delta R, if it's a steady state problem, okay, then this tells us that Na multiplied by 4 pi r square evaluated at R plus delta R is exactly equal to Na 4 pi r square evaluated at R. This is the flux multiplied by the 4 pi r square is the surface area. So the total transport, this is kg moles per second or kg per second. This is also the same thing. So whatever comes here, exactly the same thing goes. There is no generation, there is nothing. Okay? It's a steady state problem. And therefore, we can say that after linearization, this will give us the final expression that is the consequence of it after doing linearization and simplification. And now we substitute whether we want to use this or whether we want to use this. Okay, let us take the general case. We'll formulate the problem and then leave. So if we now use this, the generalized expression that r square, and this is equal to r square C d divided by 1 minus xa. That's what I think I wrote, and this is going to be ln ddr of xa. And this is, so n square expression has been substituted, r square is ours, and here I had written that what is the expression of Na, and this is equal to 0. Or therefore, we can say that r square Cd 1 minus xb xa. Constant. So we prescribe now, because we've got an equation, and if you integrate it, another constant of integration will come. So you can say that let, when r is equal to r sub a, x of a is equal to x star. When r is equal to some value of r, so we say this is, we'll make a simplification later on that when r tends to infinity, but we don't want to apply that boundary condition now. So at some other value where rb is greater than ra, we say that xb, xa is equal to xa bulk, far away from the surface of the sphere. So therefore, we can say now that if we do it like this, and the integration will give us so xs star to xa bulk, and this is ra, radius of the sphere, to a hypothetical distance where the concentration is this. We will solve this from here. I think in the next class we will proceed because it will take long time. I have taken already 45-50 minutes. So we will continue tomorrow with the subsequent discussion. And I want to show that this is a problem which we have studied in the context of heat transfer, if you remember. And in the heat transfer case, we had an equation like exactly saying this 1 minus xa factor was not there. Okay? And there, if you remember, that we had derived that Nusselt's number is equal to 2. But we will see that the two cases that we have determined or we have considered, one is sparingly soluble when a pure diffusion case comes, that is exactly akin to the heat transfer, and we will find out that corresponding the mass Nusselt's number, this is Nusselt's H, and I will say a mass Nusselt's number will also come out to be 2. This number we call as Sherwood's number, that we will see later on. But when you have a bodily transport term, we will get some additional factors on top of 2, and that I am going to discuss in the next class.